Hey guys, welcome back to my channel. So in this video, by the way, I'm in the middle of the Sri Lankan jungle, so there's quite a lot of background noise. There's a school over there, so I hope the sound is clear. I'm going to do a quick video today on script, so Bitcoin script and Bitcoin locking and unlocking scripts, which are written in this syntax called script, right? So in this video, I'm basically going to take you through the syntax. The basic syntax and the concept of script, which is a stack-based execution language, when it runs, where it runs, and then also about the concept of locking and unlocking transaction outputs. And this all ties into the last video, so if you haven't seen that, then please probably watch that before this one, and this diagram is probably familiar from that video, where we saw that there's a school bell going, so hopefully it should quieten down in a second. So we saw that down here in this diagram, we were tracking some basic cash transactions between individuals, and we were using these paper slips to track the propagation of coins and notes from one person to another using transaction inputs and outputs. So again, if that's not familiar, please go back and watch the previous video, because this video uses a lot of that material and I'm not going to explain it twice. So there's a few insects around, so I'm going to flap around a bit. So I'm going to start by I'm just going to start explaining, because the title is about script and the locking and unlocking. I'm just going to go through the syntax quickly and how it works. For those of people who are probably, let's say, already familiar with how the value is transferred cryptographically from one transaction to another, I'm just going to go through the syntax first, but then I'm going to go back to our analogy and continue the story there and see how this script ties in with that. Okay, so with that in mind, let's get going. Okay, so what is script? What's this little lightweight programming language called script? Well, it's a language that a programming language that runs on every single node in the Bitcoin system. Every single node that listens and propagates Bitcoin transactions. You've seen these in previous videos. It's a little mesh. Lots of each node is connected to one or more other nodes on the network, and they just like a peer-to-peer network. And they listen for new transactions coming in, and then as they receive new transactions, right? So they're listening for new transactions, and as each node receives a new transaction from one of its peers that it hasn't heard about, it basically validates that transaction, right? So how does it validate it? Well, there are lots of different validation rules that the node does on the transaction, but one of them is to ensure that the UTXO, right, that's referenced in the new transaction is actually being properly spent. So in other words, and we're going to come to this later. Sorry, lots of flies flying around, but so as we saw in the previous video, we introduced the concept of UTXO, which is basically unspent transaction output, and the script, the transaction output is basically is defined in terms of a script or half a script, which has to be complemented by the spending transaction, right? And that all happens, again, this is going to become clearer later when I give an actual example, but script is the language in which the validation of UTXO and can it be spent by this new transaction. This is the language in which that validation happens. Okay, so small intro to that. If it's not clear, if you're a sort of beginner to the concept of transaction inputs and outputs, please read on or listen on, and hopefully it'll become clearer. Okay, so that's where it runs now. So what is it? So what is script? Well, it's a lightweight, right? It's a lightweight programming language. It's non-Turing complete, right? Now, what does that mean? It means that there are certain sort of control flows in the programming language which are not possible. So looping, for example, is not possible. The construction in most programming languages enabling you to go into a loop and then exit the loop or continue in that loop until a condition is met is not present in this language, right? The reason for that is primarily because they want to prevent people from creating transactions that contain scripts which cause all these nodes to basically spin off into an infinite loop, right? Because the transactions themselves contain this script, and that script is going to run on every node, then somebody wanting to bring down the Bitcoin network could basically put a clever script in there which actually goes into an infinite loop and effectively brings down the whole Bitcoin network. So it's basically non-Turing complete. It's lightweight because it needs to run quickly and efficiently on every node in the network, whether it's a supercomputer, ASIC board, or whether it's just somebody's laptop. It needs to run quickly because there are a lot of transactions going on in the Bitcoin network, and so basically it needs to be lightweight, right? Non-Turing complete, and then so it's stack based, right? Now, so if you're not familiar with that, I'm just going to go into that in a second. This is quite straightforward to understand, hopefully. So hopefully it won't be this part won't take too long. Stack based means that as the script, as the program is running, it is basically every instruction basically interacts with a stack, which is, think of it like a locally held list of variables, right? That are stacked on top of each other in a logical way, a bit like stacking boxes. And every instruction basically either operates on, puts new members on, so new values on top of the stack, or takes members from the top of the stack. So that's what stack based means. So stack based really means, so you've got a list of instructions in your simple program, right? And then over here, during the execution of that program, the program, as it executes, is continually pushing. Actually, I should draw that arrow onto the top because it can only put things on top of the stack, not the bottom, right? So as the program executes, it's continually putting values on the top of the stack, taking values from the top of the stack, maybe doing something with them and putting the result back on the stack. But the stack is just a list, and it keeps growing and shrinking, and as the program executes, it interacts with the stack, and then the stack has an initial state, which is basically empty, and a final state, which is basically whatever's left on the stack after the final execution in the program happens, right? So I'm going to give a very simple example here of a script execution, very simple, and show you at each point in the way what the stack looks like, and then that really should be that, right? So if I just do, so here we go. So I've listed the actual instructions instead of vertically. I've listed them horizontally. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 instructions. Very simple little program, and I'm going to show you what each of these means, because this covers most of the instructions that happen during a Bitcoin validation. Okay, and I'm going to show you what the stack looks like at each point during the program, and kind of hopefully after this you'll see exactly how this stack works, right? So basically, when you encounter an instruction in the form of just a number, then you just basically put that number on top of the stack, right? Now, since it's the first instruction, the stack at this point starts empty. So the stack is basically, think of it like a stack of boxes. There's just one box and it has the number 2 in it, right? Same with number 3. When you encounter a number, just pop that on top of the stack. So that 2 is already there, so we stack 3 on top of it. What add does is take the top 2 items in the stack, add them together, and put the result back on the stack. So take the top 2 and take them off, add them together, put the result back on, right? So then we have 5. Then we see the number 4, we add the number 4, right? So we have 5 and 4. Multiply, or mult, basically takes the top 2 items from the stack and multiplies them together and puts the result on the stack, just like add did, right? Duplicate, or dupe, basically takes the topmost item on the stack, duplicates it, and puts that on top, right? So now we have 2 20s on there. Add does the same thing again, takes the top 2 items from the stack, adds them together, puts 40, add the number 40 there, right? So we have 40 and then 40, and then equal, which is a very important one, would basically take the top 2 items from the stack and replace them with true if they're equal and false if they're not equal, right? So after this little program here with 9 steps, we have the value. We start with an empty stack and we end with the value true, right? So that's really all I need to say about. Well, I'll say one more thing. I'll just draw one more diagram to show you how simple, in terms of execution steps, the actual Bitcoin, the simplest Bitcoin validation for a pay to public key hash transaction is, which is the most common transaction, right? So if I just show you, so in a simple Bitcoin transaction, which is actually a script that's executed on all the nodes for a new transaction. Typically, there'll be an unlocking script, which is provided by the payer of the new transaction, and which gives you the first two parts, which is basically a signature and a public key. I'm going to go into more detail on these in the next video. Okay, but I'm just giving you an idea of just to give you an idea of the fact that this language is very lightweight, even for real Bitcoin transactions. Here we have only 7 steps, right? Only 7 steps in this validation. Then, so we basically we provide a signature, we provide a public key, so the signature goes on the stack, then the public key goes on the stack, then this stuff. This comes from the output of the transaction that's being paid. So this comes from the UTXO that is being spent in the new transaction. And this output script says, has a duplicate, so basically duplicates the top member of the stack. Then it does a hash 160, so it performs a 160-bit hash on the top member of the stack. So now we have hash of the public key. Then we put the public key hash that is paid in the UTXO is being spent. So the actual referenced value that says, please pay this public key hash, that is put on top of the stack, right? So now we have these two values that we're expecting to be the same. And equal verify, which is slightly different to equal, right? Equal took the top two members of the stack and replaced with true if they're equal and false if they're not equal. Equal verify basically suspends execution of the program unless the top two members of the stack are equal, right? So in this case, we proceed as long as these two are equal, right? Which we expect them to be. Again, I'll go into more detail on why that is. Then we just remove them from the stack and continue. That leaves public key and the signature, which are the two variables required to perform check signature. Check signature, again, I'll go into more detail in the next video, but it's an operation that checks the digital signature that's been applied to the new transaction. If that will return either true or false, and the Bitcoin node, right? The Bitcoin node will agree to sign off the transaction as a valid transaction, as long as this value down here is true, right? So as long as this value is true, then all these nodes up here will consider at least this part of the validation to be correct, right? And that's really all I want to say for now about the script, because the main part of this video is basically how does the stack-based execution language work, and how does that actually apply to the Bitcoin validation. I'm going to give you an example, just an introduction to the Bitcoin validation, right? So in the next part, I'm going to delve into a little bit more about our analogy about the slips and the transfer of value between people, and tie this concept of locking and unlocking into that. So as I mentioned in the previous in the intro, so in the last video we talked about this diagram. Hopefully is familiar. We talked about using these slips as a way to audit and just record the transfer of physical notes and coins between people, modeled as transactions with inputs and connected outputs, right, which were then stored securely in the blockchain. So in our analogy, it was just a stack of boxes. A better analogy would be a duplicated stack of boxes held by different people and maintained, but still a stack of boxes containing paper documents that list every transaction, every transfer of physical notes and coins between people in the economy, right? And that's and we used inputs and outputs to track that. Now, I left you with a parting thought, which was, what if we could find a way to basically use the blockchain and use these transactions to actually do away with money altogether, right? So let's first remember. So at the end of the last video, we introduced the concept of unspent transaction output, UTXO, right? And we said, okay, using the blockchain, how can we figure out that Bob is currently carrying or has in his possession, or his wealth is £1, right? Because we look at all the transactions that he's been involved in, and look at all the notes he's received in the past, and whether he's used those notes yet in subsequent transactions or not. And we were able to deduce, just from looking at the documents, right, that were in the blockchain, that Bob has an outstanding wealth of £1 in the form of this £1 coin, right? So that's very important, right? The unspent transaction output was a way to at that time, in a cash-based system, how much cash each person actually has in their possession. So so let's say on this day here, right, the day that Bob gets this £1 coin back. So we're continuing the story. Let's say that there's a decree that says, right, guys, we are no longer going to be using cash in society at all, right? And we're not going to be using bank accounts either, right? So forget about bank accounts and HSBC and all that kind of stuff. We're not going to be using coins, bank accounts, or notes or whatever. We're going to be using blockchain transactions, right? But for the time being, let's forget about Bitcoin. We say the unit of value of wealth is still GBP, right? It's still, because these coins, these transactions were all denominated in a unit of value of pounds, right? There was a £1 coin, there was a £5 note. So all we're suggesting at this point is that the value itself will be encapsulated and transferred using these documents, rather than being just recording transactions and transfers of real coins and notes in the outside world, right? So so basically, and at this point, so let's say on this day, there's a decree, right, that goes out over the whole town, right, that says, right, everybody, hand in your notes and pounds, because from today onwards you can't spend them, right? Straight away, Bob and all these other people are going to be up in arms. They're going to be like, well, I earned this money. This is, this is mine. And at this point, the blockchain police up here would have to explain, listen, Bob, chill out, right? Your value, your wealth is safe, right? Hand over that £1 coin, because from today onwards you can't spend it. However, we know from the blockchain, looking at the unspent transaction outputs already, we know that your wealth is £1, right? So hand over that £1. The blockchain is safe. It's a safe and completely indestructible, untamperable audit trail of transactions between people. And this record currently shows that you have £1 of wealth, and that's your wealth, right? And we'll show how that can be spent, right? Same with Lance, same with Greg over here, same with all these people and everybody else in society. Their wealth is recorded and defined by their UTXO on the blockchain, right? Their unspent transaction output that is basically tied to them. Okay, does that make sense? So we're going to tie this back to the locking and unlocking scripts in a second, right? So basically, at this point, everybody's a bit sort of, ooh, okay, well, that sounds a bit weird, but so I understand there's a safe record of my wealth in the blockchain. That's fine. So at least there's an audit trail of how much my wealth should be. But that's all well and good. How do I actually go and spend this £1, right? How do I spend this pound? Because I don't have coins or notes anymore. And the answer is, and I sort of hinted it in the last video, that if we allow people to write new documents, right, and highlighting this one here, to write new documents themselves, which references UTXO, right, and then binds that UTXO to a new recipient, right, and then post that new slip into the blockchain. That in itself is a way to transfer the value from Bob to whoever he wants, right? just by creating a new transaction document. So if we just zoom in a little bit more on what this new transaction might look like, right? So let's say Bob over here he was on his way to the sweet shop, to Sam the sweet shop, right? And he wanted to he was going to spend that £1 coin on a truffle, right? Sam does great truffles. He was going to spend that £1 on a £1 truffle, but on his way, he heard this decree from the blockchain police saying, "Hand over your money now. All transfer of GBP value is now going to be done using blockchain transactions," right? So at that point, he had to go. He went to hand in his £1 coin, but then the blockchain police said, "Okay, don't worry. You can still go to Sam the sweet shop, right? And you can still get your truffle. And instead of handing a £1 coin over, all you're going to do is you're going to write a new document yourself, right? You're going to write a new document yourself with a unique transaction ID, right? That's unique in the whole world, right? So crazy, crazy long random number or whatever, or an incremental count or whatever. And you're going to fill this out in exactly the same way that our previous cash audit transactions were. So inputs on the left, outputs on the right. And in the inputs, so remember that pound you got. Find out what UTXO in the blockchain that represents, right? We know that was from transfer F because that's what we used to figure out that Bob was in possession of a £1 coin. So Bob looks in the blockchain and says, okay, my UTXO says I have £1 of value left over from transfer F when I got that £1 value back from Chris. So I'm going to reference this in the input section, right? Because that was payable to me. And for the outputs, I'm just going to say pay. So the output is Sam Sweets, and the amount is £1, right? At that point, I just basically have to post that slip. I don't give it to Sam Sweets. I post it to the blockchain, right? And then as soon as Sam Sweets sees that transaction has been accepted and stored in the blockchain, then Sam Sweets basically can see that this now becomes UTXO for Sam Sweets, right? So now Sam Sweets can write a new transaction, right? Transfer H, where he can reference transfer G, output 1, and he can pay someone else, right? So this is Sam Sweets doing this because the outputs from transfer G are locked to Sam. Now, how that locking happens is something we need to talk about, right? Because you're probably saying, well, okay, if we're using the documents as the actual value store, then how do we ensure that only Sam? We know that that only Bob, for example, was the recipient of transfer F. But how do we ensure that Bob is the only one who's entitled to create this? How's the system enforce that? So, and that's basically how we need to talk about how the outputs are locked, right? The outputs in a transaction are locked, and they can be unlocked by certain specific users or certain specific criteria, right? Often it's a user, right? So in a typical Bitcoin transaction, for example, you'll see the Bitcoin address listed here, which means that only the owner of that Bitcoin address can unlock that UTXO, right? But the point is the outputs of one transaction are locked, right? So when you create a new transaction, you're referencing a previous transaction output that is locked to you, and that's what defines that as UTXO that is locked to you, right? Then you create a new transaction and you lock the output of that transaction to someone else or some other criteria, right? Which can then be unlocked in the input section of future transactions. And that is how the value is transferred from one person to another. So I'm going to take this back to the actual unlocking and locking script, right? And I'm going to say, give a slightly silly example. You're probably used to silly examples by now. So let's say that. So just let's say instead of paying Sam Sweets, right? So let's say Bob decides, you know what, I'm not actually feeling hungry right now, right? I've got £1 worth of UTXO, and do you know what I'm going to do? I am going to basically just set a puzzle, and anybody out there who solves the puzzle wins this £1 worth of value, right? So, and it works as follows, right? And this is where the locking and unlocking script comes in. So I hopefully you're staying with me. I know it's a bit involved, because what we're trying to do is build the level of comfort with the idea that these transactions can be used to transfer value without any physical medium whatsoever changing hands, and without any balances, right? So Bob, let's just take for granted, right? Take it as read that Bob, sorry, it's a bit jerky. Bob has this £1 of UTXO to spend, and let's say he creates a new transaction, so transfer G, and he creates it as follows. So the output is, instead of Sam Sweets or a name or whatever, because in actual fact, as we've seen, names don't work because they don't actually enforce that only one person can spend it. There are lots of Bobs in the world, for example, and that doesn't work. So if we go to our transfer G, and Bob is writing this new transaction, right? He's creating a new document. He's saying, okay, I'm spending this output here, right? And I am going to pay as follows. So the output is £1 of value, because that's the value of the input, to whoever can solve the following puzzle when they reference this output in a transaction input. In other words, if anybody can solve the following puzzle and reference this transaction output, transfer G, output 1, providing a solution to the following puzzle, and I'll write it in a second, then they will be able to reference this UTXO, right, and therefore spend this UTXO, right? The puzzle is as follows, and it goes back to our script, right? It's provide a script, so provide leading instructions. Let's zoom in a little bit, such that these leading instructions here, in the script language at the beginning of the video, when placed in front of 3, add 5 equals, evaluates to true. Right? So this goes back to our script at the beginning. They're saying, so it's like setting a puzzle. It's saying, it's inviting anybody out there to provide a sequence of script transactions that, when placed in front of 3 add 5 equals, evaluates in the stack-based language to the value of true on the stack at the end of execution. Only one value, not the top value, but the only value. Right? Now this is called a locking script. This is the invitation to create an unlocking script. And the locking script is said to lock the UTXO. It's said to lock the transaction output. So at that point, Bob posts this new transaction to the blockchain, and there it sits, right? Then, because this output is not tied to anybody, like no other person in particular, it's just tied to whoever can solve the following puzzle. That means that anybody, because the blockchain is open and can be inspected by anybody at any point in time. Let's say Mike, the mathematician. Right, let's say he just enjoys. I'm not sure if I spelled that properly. Let's say he enjoys just basically spying on the blockchain and seeing what new transactions come in, right? And he's a clever guy as well. And he says, there's a new transaction that says £1 of value, not £1 coins, but £1 of transaction output can be referenced by anybody who can solve this puzzle, right? And Mike's a clever guy, he's a good mathematician, and he says, well, I reckon I can solve that pretty easily. So he creates a new transaction, right? And this is transfer H. So Mike is creating this transaction, and in the new system, he fills out his own inputs and outputs. He selects a unique identifier for the transaction. He writes the inputs and the outputs. And the input section, he says what he has to do is he has to say, first of all, which transaction output are you referring to? So which UTXO, because this output has not yet been spent by anybody. Mike is the first person to spot this. He says, okay, so transfer G, output number 1. This is the output they're referring to. But now, instead of just referring to the input, he also has to add the unlocking script, which unlocks the locking script, right? And his solution is as follows. He figures, well, okay, so 2, and then if I just put 2 in front of 3, add 5 equals. So this is what Mike adds, and then this is the locking script, and this is the unlocking script. So he provides 2. So then the stack looks like 2, and then 2, 3, and then 5, and then 5, 5, and then after equals, it is, lo and behold, true. So he solved the puzzle. So all he has to do is to say, so my unlocking script is 2. Right, so he not only specifies the input that he's spending, he actually has to specify the unlocking script as well. Now, normally we've seen, okay, transactions just go straight into the blockchain, right? We talked about these slips, they just get created, they go to the blockchain. But now, somebody has to evaluate this puzzle and say, actually, has Mike successfully solved this? So before putting this in the blockchain as a valid, sealed for till the ends of time transaction, it needs to be validated by a team of validators, right? And these are like the Bitcoin nodes on the system, right? But let's say these are a team of validators, So before submitting this transaction to the blockchain, and by the way, if you're wondering what happened to all the other transactions in the past, yeah, we'll come to that. I mean, the point is, because every transaction depends on previous ones, at some point you have to introduce a new concept. So I'm aware that this transaction here, there's a slight sort of inaccuracy there. So we'll cover that in a second. But I'm aware that this is the first transaction that really looks like the proper new transaction type that we're talking about, that actually transfers the value from one person to another using the transaction documents, not the cash. So we have this team of evaluators, and they all take it in turns to basically check that the solution, the unlocking script that Mike has submitted here, does in fact unlock the puzzle, the locking script, which is 3 add 5 equals, and that does indeed come out with a value of true at the end of it. So these guys all check the document, right? And they all say, yep, looks good to me. Like, great job, Mike. So the document goes into the blockchain. Now let's figure out what's happened at that point. So now transfer G, output number 1, is no longer UTXO, right? It's not UTXO because now there is a new transaction in the blockchain which references transfer G number 1. So this output has now been spent, right? It's been spent, so Bob can no longer reference this. So sorry, nobody else can come along and create a new transaction that's referencing this output, right? So what we haven't covered is in transfer H, right, where Mike the mathematician is solving Bob's playful little transfer G over here, where he's not actually transferring this to anyone in particular, he's just setting a puzzle. What if Mike wants to then spend this money and send it to somebody else? So how do we create a locking script that can only be unlocked by a particular person, not by any person who can solve a random simple mathematical puzzle, but how do we create an output that can be only spent by a particular person? Okay. So these locking and unlocking scripts. So this is the unlocking script. Right, and this is the locking script. So from now on, all transactions will have locking scripts and unlocking scripts. This is so that this is to restrict who can actually spend that transaction output in subsequent transactions. Right. Now, one other step I didn't mention, which is related to this, is that on the day that we remove this cash from society and start using transactions to actually not only record and report wealth, but also to transfer wealth, what we have to do is, and this is going back to the input from transfer G, we have to take the existing transactions in the blockchain and we actually have to tie them properly to their owner. So for example, it's no longer good enough to just say, okay, well, transfer F is payable to Bob, because, well, first of all, there are lots of Bobs in the system, and what's to stop somebody called Fred creating a new transaction and referencing the output that was sent to Bob, and just there's nothing to enforce that, right? So what we need to do is we need to take all of these historic transactions, and we need to basically do something a bit more clever that locks these outputs to Bob in this case, and locks this output to Chris, right? So that nobody other than Chris or Bob can spend it. So we can't just write their name there or their email address or whatever. We have to basically create and what it comes down to again is it comes down to the locking and the unlocking scripts, right? We need to create locking scripts for all previous historic transactions which actually lock the output to the correct individual, right? And so this has to be done for all previous transactions. So we take all the previous transactions out and we say, do you know what, we're going to have to basically replace every transaction that we've got with a similar document, but instead of just having the name there, we're going to have a locking script so that only Bob can spend the transaction spent to Bob. And then that enables people to specify their own personal unlocking scripts. When they spend that transaction output, right? And if you go back to the beginning of the video, so if you remember the beginning of the video, we looked at the sample validation script that's done on the nodes of the Bitcoin network for a very common transaction type, which is paid to public key hash. Right? So these all the nodes that are running, and this is an example of an unlocking script, which is like the solution to the puzzle, in response to a very common locking script, which is the puzzle itself set in the previous transaction output. So, and this is basically, and I'm going to go into this in the next video, because the answer is the question of how do we ensure that that only Bob, for example, can spend the transaction outputs that have been assigned to him effectively, and the answer is using digital signatures, right? And that is going to be the subject of the next video. So we're going to go into more detail about how digital signatures can be used to ensure, as using public keys and private keys, to ensure that only Bob or only the recipient of that transaction output is entitled to transfer the value, as in spend that transaction output into a subsequent transaction. Okay, so that's going to be the subject of the next video: how we use the digital signatures to actually transfer this value between specific people, effectively owners of public keys, so owners of private keys and public keys, to transfer value that way, so that only the right people can initiate new transactions in the system. Okay, so that's the introduction to scripts, locking scripts, unlocking scripts, the syntax of the language, and how it's used, how it's validated, and all that kind of stuff. Please subscribe, thumbs up and share, all that kind of stuff if you like these videos, because it's a crowded space and it's quite difficult to get the videos noticed in blockchain area. Lots of people making videos on Bitcoin. Please ask lots of questions as well. I love getting questions, and I try and answer them very quickly and in as much detail as is necessary. So please do that, and thank you for watching. I'll see you in the next video. Bye.